It's question show time. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down. I'll gather them up and I will answer them here. Once again, we've got a special guest answerer, so stick around to the end of the show and you'll see that. All right, let's get into it. Richie5903. Now that we haven't had the shuttle for almost a decade, what craft, if any, has been able to provide boosts to the International Space Station? Do the Russian capsules have that ability? Yeah, one of the jobs of the space shuttle back in the day was to help give the International Space Station a boost. And that's because the space station is orbiting so low that it's actually orbiting through a fairly thick part of the Earth's atmosphere, and it's constantly losing its altitude. And if it didn't have these regular boosts, it would fairly quickly burn up in the Earth's atmosphere, and that would be that. And so NASA and the Russian Space Agency have to constantly boost the station every few months to gain more altitude to prevent it from crashing into the atmosphere. So it used to be done by the space shuttle, but the space station actually has thrusters on board that it can use to boost itself back up. And so additional fuel is supplied by the cargo Dragon, as well as these Russian Progress cargo spacecraft. And so they'll deliver, often they're completely automated, and they'll deliver a whole bunch of fuel and food and water and air and a lot of other supplies, and the space station can use that fuel to boost itself up. And if it doesn't use that, it can also be boosted up by the spacecraft that are attached to it. And so this is often done by the Progress spacecraft. They can fire their thrusters and boost the whole space station back up again to prevent it from crashing into the atmosphere. XJohnny1000. The name dark matter is the cause of the skepticism. Might as well have called it magic space glue. Neutrinos never had this problem before they were discovered because they came out of the gate with a non-ridiculous name. I think that's a great point, that a lot of the scientific issues that are some of the most fascinating also have ridiculous names. Dark matter, dark energy, black holes, Big Bang. And maybe if they had a more, I don't know, sciencey sounding name, like gravitational waves, right? Does anybody have a problem with gravitational waves? And yet these are caused by mass moving, by black holes colliding together, by neutron stars colliding together billions of light years away, and they're waves washing over the planet. But people seem to think that's pretty cool and don't have this general skepticism. With each one of these things, they are mysteries that we understand parts of them and we don't understand other parts of them. And so if a person has a knee-jerk response and say, I don't think black holes are real, or I don't think dark matter is real, or I don't think dark energy is real, that's fine. But you have to be able to come up with an explanation for all of the observations that have been made so far. And there have been a lot of observations that have been made so far. We don't have a complete understanding of what these things are, but we have a partial understanding and awareness that they're there. And absolutely, a better name would be fine. Or we just wait as more data is gathered up until we finally understand what's going on. But that's half the fun of it, right? Is to be part of this mystery, to watch as the pieces come together, to hear about a new experiment, a new observatory that's going to be going out to try and understand parts of the problem. And I feel like when people have like an off the cuff, I don't think that's real, they literally don't even understand the state of the search for these ideas, for the evidence so far. And anyone who understands the evidence gathered so far then would feel that it's a more compelling mystery than just I don't think it's real. But yeah, new names would be better. Michael De Maria. Great episode, but Dr. Hinkle didn't answer the actual question about having a solar system of planets orbiting a non-star object. So the rather cool question remains about a solar system orbiting a massive object that isn't an actual star. We'd love to see that one get answered. Sure, so in last week's question show, the question was, could you get essentially a planet forming without a star? And this is this idea of a rogue planet. And the answer is absolutely, right? Wherever you have gas and dust collecting together, it's going to get to a certain point. It's going to have hydrostatic equilibrium. It's going to form some kind of spherical object. And if it's not near a star, then it's just going to be a planet. It might be a brown dwarf, or it might be like a Jupiter-sized planet, or maybe even something a little more rocky, and it'll just float in the Milky Way on its own. But the question is, could you get planets around something that isn't a star? Well, the only other objects you could have would be some kind of degenerate star, like a white dwarf or a neutron star or a black hole. And each one of those were a star in the past. So what you would probably have is you would have like a star, like a very large, very massive star, lives its short life, explodes as a supernova, and then collapses into a neutron star or a black hole. And any planetary system that was around it would suffer damage. In some cases, they would just be obliterated. They might the planets might get consumed as the star is expanding out to form like a red supergiant, and then it collapses down into the black hole. But in theory, if the planets were far enough out when the whole thing formed, and if they could survive the shock wave from the supernova, then you would still have objects orbiting around the black hole or the neutron star. And so there's no reason why it couldn't happen. You just wouldn't want to live there. The other thing that's kind of neat is you can imagine things like, say, a star like our sun turning into a red giant and then dying as a white dwarf and cooling down. And in many cases, as the shape and the density of the star changes, the planets will shift on their orbits. And so you could end up with a white dwarf star ending up with planets orbiting around it inside the habitable zone, where they could still remain warm enough for liquid water to be present over fairly long periods of time as the star slowly cools down until it becomes the background temperature of the universe. But you would need very special conditions for that to happen. But it's certainly possible. I think planets have been potentially detected around white dwarfs, or the rubble of planets crashing into each other around white dwarfs. So there's hope, even after the sun dies. The Aaron LC. What was the telescope you told us about that has motors in it so that you can dial into what you want to look at and it finds it? The general technology for that is called a GOTO telescope. And so typically all the manufacturers make a version of this, and it's a telescope with a computerized mount. And then you have either some kind of controller, or you can control it with your computer. And then you set up the telescope, make sure that it's all nicely aligned, and then it's as simple as you just say, I want to see Saturn. And as long as Saturn is up, the telescope will turn and show you Saturn. But for anyone who owns one of these GOTO telescopes, that simple version that I just described is hardly ever the case. The more common case is you go outside and you try to set your telescope up and you can't seem to get it polar aligned, and there's people around and they're waiting for your telescope to work, and you're like, just a second, and then you give up and then you just start manually controlling the telescope. There's some people who can like polar align their telescope nicely in 10 minutes, 15 minutes. It's never been me. It's always been an hour of me messing around and then giving up. So if you want to just get into astronomy, I always recommend that you start with the Dobsonian telescope. They're completely manual. They're very easy to turn around. And if you see some bright object in the sky, like a planet or the moon or whatever, you can be pointing your Dobsonian at that object in 5 seconds. And then, focus the eyepiece and you're good to go. So for people starting astronomy, I always usually recommend the Dobsonian, and then as you have more experience and you kind of just don't want to go through the hassle and you're willing to go through the pain of aligning your telescope every time you want to use it, then go with the GOTO telescope, because once it is aligned, then it's a beautiful thing. You just go Saturn, bzz, Jupiter, bzz, the moon, right? Orion Nebula, the telescope just turns, you just take pictures or look with your eyepiece. So, and they're often like a little more expensive, but after a while, that expense becomes totally worth it. So if you're willing to deal with a very finicky technology, try a GOTO telescope. And of course, the GOTO telescope manufacturers will tell you they've solved all these problems and they're getting better, but it's still, in my experience, always a hassle to use. Mit Yelsub. I know astronomers use the stars dimming to tell if they're planets, but I would like to know, how do they know that it isn't dimming that's caused by sunspots on the star's surface? You're exactly right. When a sunspot appears on the surface of a star, it is going to dim the brightness of that star. It does it to our own sun. It's going to do it to some other star that we see. And it would absolutely fool an astronomer into thinking they're seeing the dimness that's being caused by a planet passing in front of the star. So this is something that astronomers have to be concerned about. There's a couple of ways that they deal with this. One is a sunspot takes quite a while for it to pass across the field of view in a star. So, for example, when we see a sunspot passing in front of the sun, we're looking at often weeks for the amount of time it's going to take from our perspective for objects to move across the surface of the sun because the sun is rotating. While, say, when you're watching a transiting planet, it can happen very quickly. It just takes a very short period of time for a dip in brightness of the star for the planet to pass in front. But the other thing is that it's all about the regularity, and that's why astronomers want multiple observations to confirm that, yes, indeed, it is a planet that they're seeing. So if you see one dimming of the star, then that could be a sunspot. And then if the dimming is perfectly aligned with the rotation of the star, then you know that you're probably dealing with a sunspot here. But if you see something pass across and then some period of time later, 22 days later, you see another dimming, and then 22 days later, you see another dimming, and then 22 days later, you see another dimming, then you know that that can't be a sunspot because sunspots come and go. So the more observations that you can make, the more you can rule out things that aren't planets and like sunspots, etc., and be more and more certain that what you're looking at is a planet. And that's why trying to be able to see planets that are quite far away from their star, say one that takes a year to orbit around their star, like the Earth would, that is going to take 3 years, 4 years, 5 years of observation. So even once we've got the kinds of technology that can detect those kinds of planets, it's going to take a long time for us to be absolutely certain that we are seeing a planet in those kinds of orbits. So I guess be patient. Richard Gabriel. Do you think that we could ever achieve interstellar travel without the creation of wormholes? People talk a lot about how the speed of light is the fastest, but even though we can travel at the speed of light, it can't really get us anywhere, considering the size of the observable universe. Science fiction has really spoiled us. We think about the size of the universe, that there are hundreds of billions of stars located in the Milky Way, and it is hundreds of light years, hundreds of thousands of light years across. And we're like, we want to visit them all. And Star Trek and Star Wars tells us that we should eventually be able to have this empire that spans the entire Milky Way. But we can only do that if we can go faster than the speed of light. And as I mentioned many times, it probably going faster than the speed of light is going to be impossible. So wormholes are this idea that maybe you can connect 2 points in space-time together and be able to travel through that instantaneously. The mathematics says that it's possible, but just because the mathematics says it's possible doesn't mean these things are really possible in real life. And it could very well be that the same mathematics that says they're possible says they will completely collapse if anything tries to go through them, like us. And so the larger thing, like this is, we have to be okay with the possibility that we will never have a way to quickly travel from star to star. That any attempt to move to another star will always require us traveling less than the speed of light. Now, maybe we can go 10% the speed of light, 20% the speed of light. So it only takes, say, 40 years to go to Proxima Centauri, 20 years to go to Proxima Centauri, which is the closest star, and would take millions of years to cross the Milky Way itself. And I know that sucks, and that might just be the way the universe works. The universe is gigantic, we are insignificant, and we will probably never know everything about it. And that just makes it amazing and terrifying and sad and exciting all at the same time. So once again, just remember that science fiction is messing with your expectations of how the universe really is. Taryn Hundal. I don't really understand why people want to make Mars habitable if the cost of restoration is that much. If we are willing to go to such lengths, why can't we just restore our own planet? That obviously will be much easier than restoring a whole new planet without water and atmosphere. Absolutely. If we can't get a handle on managing the environment here on planet Earth, which is where we live, we don't stand a chance of doing something as complicated and as intensive and long-lasting as attempting to terraform an entire other planet like Mars. We can't do it. There's no way, right? That if we can't just like lower our greenhouse emissions just a little bit, then there's no way we're going to be able to do that. But, I mean, I've mentioned this in previous videos, like just because someone says, here's an interesting way that you might want to try something, that doesn't mean that it's a feasible idea or that anybody has any plans to do this at all. And it doesn't hurt to think about it, to use your imagination, right? To take a really challenging problem and go, okay, I understand that that's literally impossible, right? But what if you could? What would you do? How would you do that? What are some ways? And sometimes when we think about the things that are impossible, sometimes we figure out a way to make them possible. And sometimes we figure out a way to do something that is more practical for our own personal lives. And so by studying, say, the atmosphere of Mars and learning about how a planet lost its atmosphere and went into a catastrophic environmental collapse, it gives us some clues about what we might face here on Earth. We look at Venus and look at about a runaway greenhouse effect and wonder how we could stop a runaway greenhouse effect. It makes us think about how we're going to have to deal with a greenhouse effect here on Earth. So I think it's always fine to imagine and to think about big problems and wonder about clever ways that, you know, it's only your imagination. What is wrong with thinking big thoughts? Practically doing things in real life, that's the challenge. That's where things get really hard. But the first step is to use your imagination. Scott Whedon. Have we mapped the surface of Venus like we have with Mars? If not, what kind of technology would be able to penetrate the thick atmosphere and clouds? No, we have a much better map of the surface of Mars than we do of the surface of Venus. The only spacecraft that has mapped the surface of Venus in great detail was NASA's Magellan spacecraft that went there in the late 80s, early 90s. And it used a radar system to map out the features on the surface of Venus down to a resolution of 100 meters. And so when you look at these images of Venus taken with Magellan, you are looking at things that are as small as 100 meters. When you compare that with the level of observations that have been done on Mars, you're looking at resolution down to 1 meter in some cases. So there's a vast difference between how well we can map the surface of Mars and how well so far we've mapped the surface of Venus. Now there have been plans to do a better mapping of Venus, and that would be amazing. There was a proposal for a spacecraft called the Vox Orbiter that could map the surface of Venus down to a resolution of about 15 to 30 meters, but that spacecraft has never flown. So I hope at some point in the far future we will have another spacecraft sent to Venus with a better technology for mapping the surface, and it would tell us a tremendous amount about what's happening on the surface of Venus, help us understand what happened to the planet, and try to figure out what are the most interesting places that we go and try and send maybe a future lander or even rover. Kyle Hunt. What would the gravity be like on a large flat disk? If I could stand on it, which direction would I be pulled in if I were at the middle or on the edge? And on the surface of a sphere like the Earth, am I pulled in different directions towards each part of the sphere or just towards the center? When you stand on the Earth, you are being pulled by the gravity of each individual atom that makes up planet Earth. And so when you're on one side of the Earth, the vast majority of those atoms are all collected on the other side of you, and they are pulling you towards them. And what it sort of overall feels like is that you are being pulled towards the center of the Earth. But if you were, say, on the top of a mountain or on the side of a mountain, or there was some part of the Earth wasn't completely symmetrical, then you'd be pulled a little off to the side. Now, if you were standing on a great big disk, a flat disk, if you were standing right at the very middle of the disk, say at the part that if you spun the disk, the part that would be perfectly in the middle, then gravity would feel kind of the same. But as you started to walk towards one edge of the disk, it would be sort of like you were trying to go up a mountain. It would get steeper and steeper as you go. And finally, when you reach the very edge of the disk, it would be like you were trying to climb a cliff, perfectly vertical cliff. And if you could stand on the, like, imagine a coin, you could stand on the edge of the coin, then you would be getting pulled down to the center of the disk. But really, the only place you could stand on a disk that was pulling you with gravity and things would feel kind of the same would be at the very center of the disk or when you were standing on the edge of the disk. Anywhere in between, and you would feel this weird pull more to one side that would be like climbing a hill as you went up to the edge of the disk. Master Pack. Neil deGrasse Tyson mentioned that dark matter interacts with nothing, even itself. Therefore, it can't be concentrated and ergo be a black hole. Yeah, so last week I talked a bit about black holes and dark matter going into them, and I was sort of going along in the right direction, but I sort of didn't continue that line of thought, and so I really should finish this. We talked about dark matter and sort of the search for dark matter particles and the fact that astronomers are very certain that they are some kind of particle that has no cross-section. And what that just means is that particles of dark matter don't bounce into each other in the way that gas bounces off each other and the way stars would smash into each other, right? And so when large clouds of dark matter pass each other, they pass through perfectly without bumping into each other and slowing down and creating some kind of concentration of dark matter. And so what that means practically is if you put a black hole into the middle of a cloud of dark matter and the dark matter would be affected by the gravity, it would be orbiting around the black hole. But you wouldn't get these bounce-offs, these interactions that happen with regular gas. And so when you see like an accretion disk around a black hole, that's because all of this mass, all of this matter, this hot gas, is bumping into each other and slowing down and going into this disk, and eventually it all goes into the black hole. But if you had the dark matter, it would be flying around the black hole, but none of it would be bouncing into each other to slow itself down to go into this accretion disk in the same way. That said, if a piece of dark matter made a direct hit, tried to pass through the event horizon of the black hole, then in it goes, and it gets added to the mass of the black hole, whatever it is. So in theory, it wouldn't scoop up dark matter in the same way that it might scoop up a lot of regular material, but if all of this dark matter was directed right into the black hole, then it would add to the mass of the black hole, and the black hole would become more massive, and there would be less of this dark matter in the universe. It would all just be part of the black hole. Matt Wilson. So we just found a black hole 1,000 light years from Earth. Any chance there's one closer? If so, how much closer can it be for us to be safe? Yeah, astronomers looked at a fairly well-known star system. I think you can even see with your unaided eye and figured out that there's actually a black hole in there. And they watched the way the stars were interacting, and one of them was just moving around, orbiting some invisible mass, and they realized that there's a black hole there. And the only way they knew that it was there was because it's in this complex multi-star system, and so the star was orbiting the black hole. So imagine a situation where you've got a black hole that has no stars orbiting around it. It's just free floating. And so there's almost certainly black holes closer than that 1,000 light years. And we may never know where they are, but they're going to be closer. Now, how close would it have to get to be? It would have to be within a few light years of the solar system for it to cause any kind of disruption on the solar system. We know that stars pass within tens of thousands of astronomical units within a couple of light years of the solar system every few million years, and yet the solar system has been going for billions of years and is roughly unharmed by these interactions. A black hole is going to have, say, 10 times the mass of the sun, more, but as long as it's far enough away, a few light years away, it wouldn't cause any impact on us. Now, if it gets closer, then absolutely it would start to throw planets around, it would start to smash planets into other planets and disrupt the entire solar system. But it all depends on how close it would have to get. But it would have to get very close, relatively speaking. Not 1,000 light years away. That's plenty far away. DVK ready. How can we even know the total number of stars in our galaxy when we live in the plane of the galaxy and only a few telescopes with infrared vision can see some stars on the other side? Great question, and I will pass it along to Michael Rodruck, who is one of the co-hosts on the weekly Space Hangout, and I got to run into him at the American Astronomical Society, and he was good enough to answer your question. So take it away.
Okay, so a lot of how we know how many stars or even how many galaxies are is through extrapolation. So we don't exactly measure every single star or galaxy, but we instead measure a few stars here, a few stars there, and then knowing the area that we're looking at, we can get an idea for, well, if there's this many stars over here, that should mean that there's probably about this many stars in the entire galaxy. And it's true that not every point in the galaxy has the same amount of stars, so you have to try to do as best you can, look as much as you can, and using that information from all the data that you have from looking above the plane, below the plane, then try to extrapolate from that to get the correct answer of how many stars there are in the galaxy.
All right, that was awesome. Thank you so much, Michael. Of course, you can see him every few weeks on the weekly Space Hangout with me talking about galactic astronomy, so join us there. All right, that was super fun. We reached the end of our questions. So again, as always, wherever you are on my channel, question pops in your brain, write it down, I'll gather them up, and I'll answer them here, and I'll see you next week.